Hello, good afternoon, or whatever time I suppose it is where you're watching this from. My name is Andrew Winter, and my co-author and researcher, Michael Motley, we're both from the University of Washington in Seattle. And so today we would like to present to you our developments on improving fluid structure interaction modeling of wave energy conversion devices using OpenFOAM, and in particular, we'd like to focus on the oscillating wave surge converter type of device. And we also work as members of the Pacific Marine Energy Center, which is partly based at the University of Washington, Oregon State University, and University of Alaska at Fairbanks. And so their work is all towards various ocean-related energy generation schemes, whether it be tidal turbines or wave energy devices like we're focusing on in our research. So looking in particular at the oscillating wave surge converter type of device, it is like some sort of paddle type device that as the wave motion pushes it back and forth, it drives a hydraulic actuator or a piston type pump that then drives a hydraulic motor and a generator, and electricity is then transmitted through cables to a storage facility on the shore where the system is monitored from. And you can see on the top right here, we've got an example of Oyster, very large device. You can see the size of the people to get enough force to drive the paddle enough to generate a significant amount of electricity. So a similar study kind of related to this was done in 2015 by Schmidt and Elsesser on how to use OpenFOAM for modeling oscillating wave surge converters. And you can see here we've got kind of a schematic, definitely not to scale, of their domain, and also the flap in the bottom left there, as well as kind of a little screenshot of what their computational domain looked like for their OpenFOAM model. And so we use this to get the geometry and validation data. But first things first, for doing our research, we also use the OpenFOAM open source computational fluid dynamics library. And in particular, we use the interFoam solver for the fluid solving part of the solution, which is a Reynolds average Navier-Stokes based type of a method using the finite volume method. It's multi-phase, so we've got air, we've got water, and to track the interface between the air and water and where each of them is, the volume of fluid method is incorporated into this. For the rigid body motion of the wave energy converter, we've got the 6DOF rigid body motion solver. For turbulence modeling, we've got Mentor's K omega SST shear stress transport model that he developed in the early 90s, and it's very good for bluff body flows where you might have separation around the sharp corners of the body. And so this is why this was selected. It's a very robust turbulence model if you're only going to go as far as using a 2-equation one. And our mesh was relatively small by, say, industry standards for CFD at only 1.8 million cells approximately. But this was small enough we could run on not too many computational nodes in the university high performance computing cluster, run enough simulations to kind of develop this scheme and test it and make sure it's working properly. So in the interest of time, that was used. To kind of demonstrate what our domain is here, we've got the same sketch as before, except here we're kind of illustrating what boundary names are. So we got the atmosphere, we got the bottom, wave maker at the left, and the beach at the right. And at the bottom here, we've got a very detailed list of all the boundary conditions used, but essentially all solid surfaces like the bottom and the flap are a no slip type condition. And the atmosphere is like an inlet outlet condition. Whereas the wave maker is the most unique one. This is also kind of an inlet outlet sort of a condition, but it allows for the generation of waves according to a classical wave theory. So you've got Airy or Stokes first order, Stokes second order, you know, Fenton's fifth order Stokes, so on and so forth, all the kind of things you think you would typically find For wave theories, you're going to find an implementation of it there for the boundary condition. Oh, and also you could potentially generate waves in the whole domain using this method, but we started with a free surface to match the beginning of the experiment in the paper. But the nuts and bolts of actually doing the fluid structure interaction can typically be done in 3 different ways in OpenFOAM and in general in CFD software. The first is the arbitrary mesh interface approach used by the paper authors. And this involves having a separate region of the domain that kind of slips or slides inside an outside background mesh. So you can see here a cylinder is a natural choice for having something rotate, and the flap is encompassed by the cylinder. Whereas down below, you've got a related method that's very similar. The overset mesh method, where you've got a background mesh and a completely separate independent mesh that is overlaid on top of it. And you interpolate fluid behavior from one mesh to the other, and also account for the fact that the object itself is like a hole in the domain and does not actually influence, you know, there's no fluid inside there essentially. It doesn't influence things going on. And similarly for the arbitrary mesh interface, you're always interpolating back and forth from the background mesh to inside the AMI rotating region. However, with the mesh morphing and remeshing, you don't have any interpolation except when you remesh, so it's not like every time step like in the other 2. And here you can see the morphed mesh has some skewed cells near the top and the bottom of the domain. And so once you reach a point where that gets too bad, you want to redo the mesh and get a nice vertically horizontally aligned mesh as much as possible for having an angled object, and keep going with the solution. So kind of the main things to reiterate here, why did we choose that combination of mesh morphing and remeshing? Well, we wanted to have a robust method for a large range of motion, which depends, of course, on the geometry of the object you're rotating, your mesh morphing settings, but it, in my experience, most importantly, the bathymetry. If your bottom of your bed is very close to the rotation axis of the object, the cells near that bottom bed tend to get distorted very easily. So the farther away that is, say your wave device is mounted on some kind of a foundation that extended off the bottom of the sea floor, that would be a very easy thing to model. So it's kind of dependent on that. But it has a capability to go maybe plus minus 30 degrees quite easily when nothing's in the way in that sense. The other thing is you only need to remesh when the quality checks fail, and we're going to talk more about the quality checks later, which keeps that down to a minimum instead of doing it every time step. And interpolation is also kept to a minimum because you only need to do it when you do remeshing from one mesh to the other, whereas with the overset and AMI, you need to do that every solution iteration. And the other thing is that the AMI method also required fitting the cylinder inside the domain. You can see here in their mesh image in the top left, it drops down a lot to accommodate the cylinder fitting inside. And so they had to augment the interFoam solver code to basically use a dissipation parameter to set velocity inside that region, set the velocity of the fluid to be 0. So then you can kind of have it maintain the behavior of being a fixed boundary, even though there's fluid in there, it's not really moving. So that's a whole bunch of extra work we wanted to avoid doing, as well as avoid interpolation all the time. So going through our simulation workflow, it looks kind of complicated here, lots of steps using different commands in OpenFOAM. But the main thing is that it can be broken down into 2 phases. And the first one is the case setup phase, where you're doing your meshing and setting conditions or interpolating from one mesh to the other. And in your case running and monitoring phase, you're setting up the simulation and running it, and then extracting data for post-processing and checking the mesh quality. And if you find it's necessary, you got to go back to the start and redo the setup phase again. So here's kind of a demonstration video, proof of concept of how the thing works in 2D here, and using the same geometry with the drop-down part of the bed as in the paper. You can see that near the free surface by the flap, you get these kind of jagged cells all of a sudden that aren't very horizontally or vertically aligned anymore. And when those get to too critical of an angle, you can see the surface smooths out periodically as well. And this is when the remeshing steps occur. So kind of going through the simulation workflow, break it down a little bit more so it's more obvious what's happening. First things first, every time you start over with this setup phase, you need to do a background mesh. And we used uniform mesh grading to kind of dictate where the refinement is going to be. And so we refined from all boundaries towards the center of the domain, with that sort of target being like the flap, or in the vertical direction, you're refining towards the free surface. And after that, you want to extract data of your model. So if you have a CAD model of your flap of your OWSC, you want to extract a surface, typically a stereolithography STL file comprised of triangle data points and normal vectors. And also you can further extract an edge mesh file for finer refinement around sharp corners and curves. And once you have that data, what do you do with it? Well, you come in and you use a tool like snappyHexMesh, which is going to go through 3 key steps. You're going to do the castellated mesh, where you refine around the surface first in space, then you remove the cells inside that space. After which you can do snapping, which kind of makes a piecewise linear connection of the cells around the edge and cuts off the sharp corners, so you get a good representation of the surface. And finally, you can add layers, which will put very thin, fine cells parallel to the surface for modeling boundary layer effects. There are other alternatives to snappyHexMesh. You can use foamy-HexMesh within OpenFOAM, or of course you can import other meshes from other software, but the foamy-HexMesh tool is kind of like a cousin of the polyhedral meshing in StarCCM+, is what it would be like. But it's essentially the same process, but with a different type of cell shape it's going for. And the result of such a process would be like this. You get the flap imported into the domain, and the mesh fits around it nicely. So after that, you want to set your initial conditions, and the first time around, you're going to do that. The second time around, ever after, when you remesh, you'd want to interpolate. So for our case, we mimicked the paper. So you start with a still water level and no velocity anywhere. And the waves are generated at the left boundary as I described earlier. And after that, you want to decompose your case and start running it using interFoam. And we ran for sub-intervals of 1/100ths of a second. And this is so that every 1/100th of a second, you're going to check the mesh quality and then restart the solver after that if you pass the checks. But focusing on the solver first, what is it doing? Well, it's using a combination of the simple and the piso algorithms, this pimple algorithm. And so if you're running the piso inside for the inner corrections in the gray here, versus running the simple algorithm corrections for the whole scheme inside the gold, if you start iterating multiple times, doing multiple outer corrections as they're called with the simple method, you get this sort of hybrid thing that's called the pimple method in OpenFOAM. So it's just a predictor corrector, traditional type of segregated solving approach, just with extra iterations. And so after you do that, you want to reconstruct data if necessary, which you could of course do to different frequency than the sub-iterations if you don't want to make too much data. And most importantly, it's assess the mesh quality. So mesh quality can be assessed conveniently in 2 ways by the 2 most critical parameters we found, which are the non-orthogonality and the skewness of a mesh. And so if a mesh is perfect, it's going to be like on the top left up there. And if it's the worst case scenario, it's going to be like in the bottom right. And the other 2 kind of depict each one separately. And so the non-orthogonality occurs when, if you look at the line connecting cell centers, if it intersects the face where they touch in a non-perpendicular fashion, then that's non-orthogonal. If it also further has the point that it crosses the boundary, not going through the center of that boundary, then you get skewness. So these are the 2 things that screw up the schemes in the finite volume method, which were derived originally for a very nice ordered mesh like in the top left there. So if you want to keep high accuracy and avoid unbounded solutions, this is the kind of thing you want to avoid. And so we set limits of 60 degrees and 4.0. The skewness is kind of like a non-dimensionalized version of the distance, that delta, right? That's the skew distance. And these were very conservative parameters to keep the fluid solution running very nicely, smooth and stable, since the rigid body motion part is actually the most unstable. So we wanted to keep a good fluid solution going first to help maintain stability of the whole process as much as possible. And so when you run the check mesh utility, you get out an output that's very long, but at the end you get something like this. And it essentially has like 8 to 10 checks here that tell you, depending on how you set things up, what's going on. And you can see that typically we're looking at the skewness and the non-orthogonality. And in this case, the non-orthogonality is what caused the need for a remeshing. But in general, any failed mesh check we recommend using for remeshing, because if you get bad mesh quality anywhere, the effects can propagate rapidly through your solution. So when actually doing the algorithm, check the number of mesh checks. So if you pass, keep going, go back to interFoam. If you don't, go back and redo the case setup phase and remesh, and this time you'd interpolate from the old to the new. And demonstrating our actual motion here of a paddle for one period of oscillation, you can see that by the end of this, you'll have noticed that it rotates more to the left than to the right. And this is going to be due to the fact that the waves at this point in time are only coming from one direction. There's no return flow or waves. And so it's kind of an asymmetric loading of the paddle in that sense, and response of the water behind it. And you can see that here more obviously. We have a slightly larger error on one side than the other, and also a slightly larger rotation angle on one side than the other. And the error is comparing to the extreme values reported by Schmidt and Elsesser. They also reported just one period of rotation history, but did not specify the time into the experiment and the numerical simulation that this was at. So we figured for developing the model, it's simplest to compare, does the period match and do you reach the same amplitudes? So the amplitudes need some work. As you can see, we've got about 8.5 and almost 14% relative error, depending on which side you're looking at. And this is going to be due largely to the acceleration damping that occurs in the rigid body motion model. To keep it stable, you definitely need to specify some damping, but this is clearly too much damping. And so we're also trying to optimize the level of damping so that you not only get the period to match nicely, but you get the amplitudes to match nicely as well. Since you can see the period is only off by 3.5% roughly compared to the amplitude errors. Finally, what are we doing with this work now and how are we continuing it? The first thing that's more or less in operation and being perfected is a smooth ramping of the time step from something very small back up to a value that would be determined by like the Courant number and in the solution for restarts after remeshing. And this will help smooth out the rigid body motion from being at all unstable when you restart suddenly. Also, we want to verify that key quantities are being mapped correctly and conserved nicely from one mesh to another when you do the interpolation. Like for example, does the water volume change, or does it not, hopefully? So we're in the process of verifying that over longer durations of simulation. And also, we want to perform a parametric study using snappyHexMesh and mesh quality criteria as the variables to be changed in the study, such that we can figure out for a very full range of motion of the flap, what is a good setting for snappyHexMesh to get a mesh that is high quality surrounding the flap. And also what kind of mesh quality criteria are needed to keep the fluid solution accurate enough that it doesn't negatively influence the rigid body motion solution of the flap. So that's ongoing work. And finally, the ultimate goal that's also ongoing work is to implement this approach using the foam extend fluid structure interaction libraries so we can study flexible oscillating wave surge converters instead of just rigid ones, to see if there are any beneficial or detrimental effects from that. So thank you for your time. I hope everyone's doing well, enjoying the conference, and stay safe out there.